Hello, how's everybody doing today? Today, Monday, I hope you feel strong and ready to learn a lot. Today, we will investigate the lab number 6 in Labflow, which is chemistry of copper and percent yield. One of the objectives of this experiment is to perform a few chemical reactions involving copper and its compounds. So you will be given a copper wire, and then you will perform 5 different reactions, chemical reactions. The first reaction is to add, you have the copper wire in a beaker, and you add nitric acid. Nitric acid is a powerful oxidant and is going to dissolve. No more wire is going to be in the beaker, and you will have a blue solution. And then you will continue with 4 other reactions until you recover. You get back the copper metal as well, the copper metal as you had it in the beginning. So if you were in the lab, one of the objectives of doing this experiment is to quantitatively evaluate your laboratory skills, because you start with wire, a known amount of wire, and at the end you can weigh how much copper you have at the end, and it's a way of evaluating your laboratory skills. But because this is a dry lab or virtual lab, you will be given all the data. You will be given the original mass of copper, and you will be given the recovered mass of copper, and you will be asked to calculate the percent recovery of copper. Another objective of this experiment is to recognize what kind of reaction. There are different types of reactions we went over in the previous workshop, and you will need to recognize each of the 5 reactions, what kind or what type of reaction is. Some are metathesis reactions, some are redox reactions, some are decomposition. So this is another objective of this experiment. So as we do each week in these workshops, I will give you a quick overview of the experiment, and then we'll do a learning check. And towards the end, we will go over the report that you have to complete and make sure that you have all the information you need to complete successfully the report. So I will start by sharing the page of this experiment. One thing I wanted to tell you, don't think you cannot interrupt me. Interrupt me as many times as you need. You can raise your hand or unmute yourself and ask. I would like everybody to understand everything. And also, once I stop recording, I will stay here just in case you have questions regarding this experiment or the previous experiment. So I will be available for you. Okay, so let's get started with sharing the page of the experiment. So everybody sees the page of the experiment. This is described because it's written as if you are in the lab, you can actually perform this experiment. So in the introduction, basically, they are giving you the 5 reactions that you are going to perform. So let's look a little bit at the reaction number 1. In the reaction number 1, you have, this is the copper wire, and you add, this is nitric acid to the metal copper, and you obtained copper nitrate, nitrogen dioxide, and water. Please note that this says AQ. AQ is wrong. This is a gas. Nitrogen dioxide is a gas. So it should be a little g instead of AQ. So you can correct that. So this reaction actually is done in the hood because NO2 is toxic. When we add the nitric acid to the copper, we will have a blue solution. All this copper is going to disappear and form copper nitrate, which is a blue solution. Because you are not doing this experiment in the lab, you will be given the observations. The NO2 is a gas and has a brown reddish, they're brown reddish fumes. So when you add the nitric acid, you will see those brown fumes of nitrogen dioxide. So you will need actually to learn these 5 reactions, because in the pre-lab quiz and later on, you will be asked if different questions about these reactions. For example, they can ask, what is the phase of the product when you add nitric acid? What are they referring when you said the phase? If it's solid, if it's liquid, if it's a gaseous, or if it's aqueous. We said that this is wrong. We said that aqueous here it should be a gas, right? So basically, we start with a copper solid and we end up with copper in solution, and it's a blue solution. And then the second reaction, you add a base, you add sodium, everything is in a beaker. So you have at the beginning, you have the copper wire, and you add in the beaker the nitric acid, and you end up with a blue beaker. And then what is the second? And I forgot to tell you, but we're going to go over that this is a redox reaction. We are going to, why it's a redox reaction? This is important. Why it's a redox reaction? Because it changed the oxidation state. These actually, the redox reactions are the hardest to recognize, but you can look at a few things. First of all, you basically start with a free metal, right? A free element here, copper. And then when you look, where is copper? The product side. Oh, copper is combined and it's forming copper nitrate. Okay. And then what happens with the copper? You basically, what you already at this point learn what is the oxidation number or the oxidation state of a compound. You know that there are several rules. that you will need to learn about how to find out what is the oxidation state of an atom. Basically, what represents the oxidation state? It's basically the number of electrons that any atom can gain or lose or share when it's bonded with a different atom. And the rule says, one of the rules, there are many rules, that all free elements have an oxidation number of 0. So copper is a free element, it's not combined. So copper is oxidation state 0. And what is the oxidation state of the copper in this compound, in copper nitrate? Well, we know that if we add all the oxidation states of a neutral compound, exactly, very good, Douglas, thank you, is +2. Exactly, thank you. So we know that the copper has an oxidation state of +2. And we know, because we already studied the polyatomic ions, and we know that nitrate has a -1. And we have 2 nitrates. So the copper oxidizes from 0 to +2. That's another way of recognizing that this is a redox reaction. We will go over later in some learning checks to make sure that you understand the redox reaction. Let's look at the second reaction. What are we having? We have a beaker, right? We say we have no solid at this point because all the copper solid is in a solution, a blue solution. It's as copper nitrate. And what are we doing in the second reaction? In the second reaction, we add sodium hydroxide here, a base. And what happens? This is the copper nitrate is aqueous, right? It's a solution. The sodium hydroxide is a solution. So we have 2 solutions on the reactant side, AQ. What do we have on the product side? They are giving us an S. So that means we will see a solid there. And then this is a solution. So what we are doing is forming from a solution, when we add the base, we form a solid of copper hydroxide. And that is a blue precipitate. You don't need to know because you're not doing that in the lab, but you will need to actually learn those reactions, but you will be given the data, so you will know what is the color. So we observe a blue precipitate of copper hydroxide that forms in the reaction 2. Now, what kind of reaction is that? Let's look on this here it says metathesis. What are metathesis reactions? If you remember, we went over in the previous workshop, is that positive ions switch places and get new negative ions. So basically, what do we have here? We have the copper. The copper is the positive, right? It's the first one, it's +2. So let's look at which one is positive and which one is negative. In the reactant side, copper is the positive and sodium is the positive, that is +1. And then we have the negatives. We have nitrate and we have the OH. We know that the OH is minus, and we know that the nitrate are the polyatomic ions that you need to review. So what happens in a metathesis reaction? What do we say? That positive ions switch places. Basically, the copper is bound to the nitrate that is negative, but it got tired of the nitrate, and it said, I want to switch places with the OH. There are not many options, either the nitrate or the OH. So the copper that was with the nitrate is going to switch places and combine with the OH. So and the nitrate is going to combine with the sodium. That's why this reaction is a metathesis or double replacement. So those are easier to recognize than the redox. But once you learn the rules of the oxidation state, you will know immediately if it's a redox reaction, because you will find out the oxidation state of the copper before the reaction and after the reaction. Any questions so far? Okay, so what happens in the third reaction? You add this and you produced this precipitate and a solution of sodium nitrate. And then what do you do in the third reaction? You heat. All this that I'm telling you is described in the procedure, like if you are doing it. So what you start to do in the third reaction, we heat the blue precipitate of copper hydroxide. And what do we see? This little triangle means that it's heat. We are applying heat. And we observe that the blue precipitate of copper hydroxide turns black. Why black? Because that is the color of the copper oxide. And then what happens? If you were in the lab, you will wash the black precipitate with water many times, because you only want all the copper to combine as copper oxide. You want to do this the best of your efficiency. You want to recover as much copper as you can. And then it says, there is a question in the report that you will need to answer. And it is asking, what are we removing or washing with the water? What do you think we are removing? When we have this copper oxide here, and we want to remove everything else, we only want copper oxide to continue with the reaction number 5 and the reaction number 6. So what are we removing? What is it that we don't want to have to continue the reactions 5 and 6? Can you see that? Any remains OH ions? Yes, that is true. But we actually assume, yes, that is true. But all the OHs, but we have excess of that, yes. But what happens? The OH combined with the copper. And what else if we look at the previous reaction? We had two products, right? Copper hydroxide and sodium nitrate. And then what did we do? We took the whole beaker and we heat that in order to form the copper oxide. But there is another product that is the sodium nitrate. And that is basically what we want to get rid of. Of course, there are other things, but mainly we want to wash and remove the sodium nitrate. So any questions there? Okay, so let's look at the other two reactions. What happens in the fourth reaction? They are telling us that it's a metathesis reaction. Can we see that? Yes, we can. Awesome. Yes, exactly. Emily, the answer is that for that part, but then they're going to ask you again, what are we washing in another? In that, when they ask you about that specific reaction, yes, we are removing the sodium nitrate. That's correct. Now, let's look at the reaction 4. Can we see why this reaction is a metathesis? The copper, the only option, if it's not with oxygen, the only option that it has is the sulfate, right? Copper doesn't want to continue with the oxygen. Okay, the other option is the sulfate. And then the hydrogen bonds with the oxygen to make water. So that's why this is a metathesis. And what happens in this fourth reaction? We have the black, we said that this is black. When it says S, try to be familiar with what is in parentheses because they are telling you what is the phase of that substance. So they are giving you an indication if you're going to have a solid, if you're going to have a solution. In this case, you have the solid that you wash several times, copper oxide. Okay, oxide. And you add a strong acid, sulfuric acid, to the solid, and what do you end up with? No solid. See, you have aqueous here, and you have a liquid, and form copper sulfate. So what do we observe? Well, if you were in the lab, you observe that the black precipitate of copper oxide disappears and a blue solution forms. Yes, thank you, Douglas. Exactly. A blue solution forms. And we have now copper sulfate, which is this, in a beaker. And it's a solution, no more solid. But if we remember, we want to recover the copper. We want the copper back. It was a solid, we wanted a solid. And that is going to be the last reaction. The last reaction, number 5. What do? We add zinc metal. We saw that reaction in the previous experiment. Remember when I sent the invitation of the workshop? It was a blue solution with a little piece of metal inside that was covered in kind of in a dark. That is the same reaction. What is happening? It's a redox reaction. The zinc metal is more, we say it's more active. What does that mean? It's easier to oxidate the zinc metal than to oxidate the copper. So when we add zinc metal, what happens is that the zinc oxidizes to form zinc sulfate, and we recover back our copper that we want to wait, and we want to see how well we did in the lab. After all many reactions, how much I lost, how well I did. So basically, we are going to observe a black-brown precipitate of copper. And what happens with the solution? We had a blue solution, we said, but the solution becomes colorless. Why? Because we have now zinc sulfate. We don't have any more copper sulfate. All the copper is free, is in the beaker. It's in the beaker as a metal, as a solid. When I show you that invitation in this workshop, I put a beaker. If you saw it when I said looking forward to seeing you tomorrow, there is a beaker that is a blue beaker with a black solid. Okay, the black solid is the copper, but that reaction in the picture is not done. Why? Because I can still see blue, and blue means not all the copper reduced. I need all the copper because I'm trying to do a quantitative reaction. I want to obtain as much copper as I can. So either I need to add more zinc, but I have to recover all the copper. So if this reaction, the number 5, you do it correctly, the solution of zinc sulfate should be colorless because it has no color. And the original blue color from the copper sulfate disappeared. And then one more thing about the last reaction. There is a side reaction because there is acid there. And in the procedure, when you read it, it says stop when there is no more bubbles. And we observe bubbles of hydrogen gas because there is a side reaction that basically the zinc that you add not only reacts with the copper sulfate, but reacts with the acid to form, let's say, hydrogen gas plus zinc plus 2. This is a side reaction, but I'm writing this now because there are hydrogen bubbles that you have to observe. And what is our interest? Our interest is in the copper. We want the copper. We add zinc metal, but we don't want to have any zinc metal solid in that solution. We want to oxidize all the zinc and have the zinc as zinc plus 2. The solid, we only want the copper. So that is a side reaction, and we are going to observe bubbles of hydrogen gas. And when we heat the beaker until all the zinc is consumed and no more bubbles are observed. This is, if you read the procedure, this is what it says. And then we wash the copper, which is a black precipitate. We wash the copper with water many times. I think it was the first experiment that we learned the process of decanting. What is decanting? We add water and we decant. Very slowly we leave the solid on the bottom and we pour very carefully so we don't disturb the solid in the bottom, and we remove all the impurities. And we do that, we wash that with water several times. And again, there is another question in the report. What are we removing or washing with the water? And we are removing what? The solution of zinc sulfate. If you look at the last reaction, you produce zinc sulfate and copper. So we are only interested in the copper. So we remove in this step all the zinc sulfate. Any questions so far? Okay, so the last step, if you were in the lab, is you have everything in the beaker. You wash it very well, and then you transfer the solid to a evaporating dish. Let me see if there is a drawing here. No, here I thought there is a drawing here. Let me see. Okay, here. So basically, you are going to have the copper there, and you're going to set up like that. You're going to transfer the solid to this evaporating. This is the evaporating dish, and you put it to in this setting. So in a steam bath, and all you want is to dry the copper, because you need to weigh the copper. If you don't dry the copper, well, let's go back to our calculations. If you don't dry the copper well, look at the formula of the percent recovery. You will have to use this formula. The initial mass of copper is going to be given, and the recovered mass, let's say you didn't dry the copper correctly, it's still some water. The mass of the recovered copper is going to be higher, and because the recovered water, the recovered mass of copper is in the numerator, your percent recovery is going to be high if you don't dry it correctly. That is a question that you will need to apply this concept, because at the end of the report, they ask you, depending on what you calculate, they will give you the data. And you will look at your percent recovery that you calculated with the data that was given. If you have a recovery higher than 100%, it cannot be, because it don't create matter. So there is a big chance that you didn't dry the copper properly, and that's why the percent recovery is high. But there is another possibility, that when we work in the lab, we are a little sloppy, or there is a reaction, or we didn't see and we lost some solution, we lost mass. It's normal. When I make a cake, I cannot recover everything. There is always something that is left in the pan. So if we have a recovery that is lower than 100%, means we probably lost some copper in one of the steps. So you will have to look, once you calculate the percent recovery in your report, you will look if it's higher than 100% or lower than 100%. If it's higher, there is a big chance that you, as I said, I don't want to repeat myself, but there's a chance that you didn't dry it correctly. And then here it says, don't pay attention too much about this, because it's a little, some things are correct, some things are not correct. It says metathesis reactions proceed to completion whenever one of the products is removed from the solution. This is totally true, and we know that. You study metathesis reaction, and you said that if you have gas, that is the driving force of the metathesis reaction, or if you form a liquid or a solid, or sometimes that's basically it. Now, there is a few things that it says that are not exactly happy, because it says reaction 1, it's a redox reaction, and here the way they wrote this, it's a little confusing. So it's okay, as long as you know that what is correct is here. When they are saying what kind of reaction is each one, this is correct. The one is a redox, metathesis, this is correct. And also it's correct that one of the product is removed from the solution. The formula is correct, and here they are giving a practice problem. And now my question is, would you like me to solve that problem? Why don't you read the problem and tell me if it's easy for you? It's not much about the experiment, but you will need to learn all these calculations for even the lecture. So let's read that problem. Maybe you can zoom in your computer as well, and tell me if you would like me to solve it or to continue. Do you think you can solve? Okay, no problem. I'll be happy to do it. So let's see how this problem is something that you will need to be familiar for the lecture. This is basics, and you will carry this in if you do another chemistry. This is basic. You will need to know how to solve these kind of problems. So let's read it. It says, if 3.35 grams of copper nitrate are obtained from allowing 2.25 grams of copper to react with excess of nitric acid, and they ask for what is the percent yield of the reaction. So what is the first thing when you read that problem that comes to your mind and you say, oh, what I need to do? The first thing that you need to do is to know the mass of copper, because they are not telling, like in our report, they're going to tell you, okay, what is the mass of your copper? In this case, they are telling you that you obtained 3.35 grams of copper nitrate. So it's the first reaction. And you want to know how much copper you lost in that reaction, in the first one that we saw. So we have to calculate the mass of copper in how many grams of copper are in 3.3 grams of copper nitrate. And this is our theoretical yield. And then from there, we calculate the recovery. Any questions so far? Because this is the first thing that has to come to your mind. And then how do we do when we have grams of A and we need to calculate grams of B? So basically we have grams, 3.35 grams of copper nitrate, and we need to know how many grams of copper we have. That's why grams of A to grams of B. We cannot go directly. We cannot go directly from grams of A to grams from 2 grams of B. So how do we do this? This is basic. Always, let me change the color. So you start with 3.35 grams of copper nitrate. Very good. First thing, grams to grams? No, no. Grams needs to be converted into moles. When we want to know to pass from grams of A to grams of B, always have to go through moles. So how do we convert the grams of copper nitrate into moles of copper nitrate? Well, that's easy. That's why the molar mass is there. I'm going to write CN for copper nitrate. 1 mole of copper nitrate, the molar mass, when you calculate the molar mass from the periodic table, you are going to obtain this number. So first thing, convert grams into moles of the same thing. Grams of A into moles of A, molar mass of A. Moles of A into grams of A, molar mass. Always molar mass. Now, when we look at what cancels, we have the grams of copper nitrate, the units. Always write the units. Please, if you get use of that now, then it's you're gonna say, it's gonna save you a lot of problems. Now we wanna see if the units cancel. Yes, the grams cancel and the grams cancel. Very good. Now what units survived? The moles of copper nitrate. Are we looking for moles of copper nitrate? No, we are looking for grams of copper. So instead of moles of copper nitrate, we need to find the molar ratio, because we are changing moles of copper nitrate, but we need moles of copper. And then once we have the moles of copper, okay, we can, with the molar mass of copper, we can get the grams. What is the molar ratio? If you look at the reaction, you will see that 1 mole of copper has 1 mole of copper nitrate. Exactly, 1 to 1. Thank you, Douglas. Yes. So in this case, it doesn't affect because it's 1 divided by 1. But always get used to writing, so any mistake you can figure it out what it is. So the units of moles of this cancel. Now, what are the units that survive? Mole of copper. No, we don't want that. We want grams. But it's easy to convert moles of copper into grams of copper. It's the same thing. So we have to use the molar mass. What is the molar mass? Okay, the molar mass, you find it in the periodic table. Exactly. Yes, 64. Sometimes I use 2 or 3 decimals, but it's fine. So grams of copper, thank you, divided by 1 mole of copper. And when I do this, I do all these calculations, I will find that 3.35 grams of copper have 1.135 grams of copper. This is the first step. We want to know how many grams of copper are in this. And the last step is just very, very easy. The percentage recovery, how much I recover, is going to be this mass divided by the original mass. If we look at the problem, it says 2.25 grams of copper. 2.25 grams of copper times 100. And I obtain 50.4%. They obtain, what did they say, 50.5, but doesn't matter. Might be the sig fix, but this is the way of approaching this problem. Any questions in this problem? Okay, so then I will share some learning checks before we do the report. A few problems to solve together. Yes, Emily, very good. Exactly. Thank you, Emily. That's a very good point. I lost a lot. I lost half. Yes, it's not a very good recovery. This student maybe lost a lot. It should be 100%, but no, it's never 100% in an experiment, but a little better than that. I agree. Thank you, Emily. Let's look now at this first problem. This is very similar to what you will have to do in the report. So I wanted you to be familiar with this. So it's not a surprise. It's very simple though. It says, what is the mass of copper recovered and the percent yield? Let's see. Here, percent yield in this experiment. And this is what you are going to be given. How do we calculate the mass of copper recovered? Do I need to use the initial mass of copper? No. We are talking about how much copper I had at the end. And what information are they giving us? They are giving us the ending mass of copper and the evaporating dish. And the mass, the evaporating dish, when it's empty. So how do I calculate the mass recovered of copper? Recovered copper is very simple, right? It's going to be 49.0773 grams, which is the mass of copper and evaporating dish. But we are interested in only the copper. So we are going to subtract the mass of the evaporating dish. This is what you will need to do in your report. 5 grams. And I obtained 0.5228 grams. And then the second question, it says the percent yield in this experiment. We use the same formula that they are giving us. So how are we calculating this? I have the mass recovered, and that goes in the numerator, 0.5228 grams, which is what I just calculated. And what goes in the denominator? The initial mass of copper, which is what I started with, 0.5308 grams times 100. And I obtained a better yield, which is a 98.49%. Any questions on this? Okay, let's look at the next one. There are some questions in the pre-lab quiz that ask you to recognize what kind of reaction you are having. So let's identify, that's why I put it there, the type of the following reactions and oxidation state changes in once you find a redox reaction. Let's look at A. Pay attention to A and tell me what type of reaction is that one. Yes. But we call it what kind of single replacement? It is a single replace. We call it also redox. Yes, exactly. In general, these are called redox because on the only reason, but it's a single replacement as well, because we get a free element that is different from the free element that we had at the beginning. Let's look at the oxidation states. What is the oxidation state of zinc? Correct. What is the oxidation state of zinc? Suppose, let me see this question. So both single and double no, replacement are not redox. No, never be, because they only switch places. So redox are the reactions that you will see that the redox changes the oxidation state. But let's look at zinc in the reactant side. The reactant side, because of the rules of the oxidation state, says, what does it say? That all free elements have an oxidation number of 0, including if you have a diatomic gas like that, the oxidation state with a free element is going to be 0. It's just a free element, even though you have this element, oxidation state 0. So here we have a free element zinc, the oxidation state is 0. What is the oxidation state in A, in zinc sulfate? What is the oxidation state of the zinc when it's bonded to sulfate? Very good. Awesome. +2. And so we know the zinc went from 0 to +2. Because +2 is a higher number than 0, we say that the zinc oxidizes. Let's look at the copper. What is the oxidation state of copper in this compound? In copper sulfate is thank you, very good, it's +2. And what is the oxidation state of copper as a free element? In 0, thank you. So the copper went from +2 to 0. we say, because +2 is higher than 0, we say that the copper is reduced. The copper is reduced. So this is a redox reaction. Very good. Let's look at B. What kind of reaction is that? It's going to be a redox if the elements, if you see a change in the oxidation state. Zinc went from 0 to +2. Then it's a redox. Let's look at, just for fun, at the reaction E, the last one. What is the oxidation state of the barium here in barium chloride? What is the oxidation number of barium? We know that barium is exactly +2. Thank you. Is group 2. And group 2 is always going to have an oxidation state of +2. Because we said is the number of electrons that an atom can gain or lose or share when it's bonded to another atom. So barium is easily losing 2 electrons to reach the octet. And let's look at the barium on the other side, on the product side. What is the oxidation state of barium when it's combined with barium in barium sulfate? What is the oxidation state? Douglas says 0. Why is 0? We said that barium only is 0, or any element, if it's a free element. What is only going to be 0 with a free element? That means it's not bonded to anybody else. Like here we say zinc is 0 on the reactant side because it's not bonded to anything. But the barium is bonded to the sulfate. So what would be the oxidation state here? +2, exactly, thank you. So we have barium +2 and we have sulfate -2, which means that the barium didn't change the oxidation state. +2 to +2. If we look at the sodium, sodium did the same. Here we have a +1, and here in sodium chloride, 1. It didn't change the oxidation state. So reaction E can never be a redox reaction. What kind of reaction is the reaction E? Are they switching partners? Just look. Barium is bound to the chloride, right? But it's tired of the chloride. The other option is the sulfate. So they switch partners. And the sodium goes with the chloride. What kind of reaction is this one? The E reaction. What type of reaction when they switch partners? Yes, thank you. Perfect. The reaction E is a double placement or metathesis. We know that the positive ions switch places and get new negative ions to form a new compound. Very good. So 2 ways of looking at that. No change in the oxidation state. And we said that this one we said is a double replacement. Very good. How about reaction B? Take a look at reaction B and tell me what kind of reaction is that? Are they changing the oxidation state? We said that free elements have free elements not combined with anybody. The oxidation state is 0. So here, the chlorine gas in the reactant side, the oxidation state is 0. How about in the product side? The oxidation state is -1. Yes, thank you, Douglas. Exactly. The reaction B is a redox as well, because there is a change in the oxidation state. What is the change? The chlorine went from 0 to -1. It was reduced because -1 is a smaller number than 0. And how about the oxidation state of bromide? Bromide here has a -1, and in the product is a free element. It's not combined with anybody, so the oxidation state is 0. It went from -1 to 0. The bromide is oxidized. So that's why when they change the oxidation state, they are redox reaction. Any questions so far? Okay, so let's go to the C. What kind of reaction is C? Who can tell me? When you see a free element and here an element that is combined, see here the nickel? Yes, here it says decomposition. I'm talking about this one, the C. And decomposition is actually the D, because the D is when you have just one reactant, and on the reactant side, on the left side, you have just one reactant, and that substance breaks down into more than one substance, in simpler substances. So let's look at C again. We are trying to see what kind. Yes, it's a redox again. Exactly. Thank you. Yes, redox again. Exactly. Very good. This reaction is a redox. How do we know it's a redox? First, we look at the reaction at the beginning and we say, here is nickel by itself. Free element is not combined to anybody. Here the nickel is combined to the chloride. Right there, you have a change in the oxidation state. The nickel here is a free element, has a 0 oxidation state. And here, when it's combined, has a +2. So the nickel is reduced. Who is oxidized? You have magnesium here as a free element, which means the oxidation state is 0. When it's combined, the oxidation state equals +2. So the magnesium is oxidized. Any questions so far? I put 3 redox because I know redox are the hardest to recognize. So I wanted to make sure we go over those. And let's look at D. D is easier to recognize because you look how many substances you have on the reactant side. Well, we have here just one substance, copper hydroxide, that decompose into two substances. When one substance breaks down into simpler substances, that is a decomposition. Decomposition. So in this Labflow experiment, you will be asked in the pre-lab quiz to recognize some of these reactions. Any questions so far? Okay, so let's go and look at the last problem before we go to look at the report. But by now, you already know basically everything, but we'll go over. So identify the phase of the copper product after you add nitric acid. This is a question that they also like to ask. Because you are not in the lab, you will have to imagine basically what is the phase. When they say phase, basically they are thinking about if it's a solid, if you have an aqueous solution, if you have a gas, but they say the phase of the copper product after you add nitric acid to the wire copper. So become familiar, all the reactions are written in your procedure. So you have the reactions. In this case, they are asking for this reaction that you have it. When the copper solid reacts, so all you have to do is look at the reaction. The nitric acid is a solution. And it's going to do, this is the reaction number 1, copper nitrate, that is aqueous. We said that we are going to have a blue solution, plus nitrogen dioxide, that is a gas, plus water, that is liquid. This reaction is given, is the number 1, the first step, the first reaction that you are going to do. So what would be the answer? Identify the phase of the copper product. Which one is the copper product? The copper nitrate. We are on the right side of the arrow. It's a product, and it's copper product. Is the copper? Yes, Douglas, thank you. So the answer to that question is aqueous. Study the 5 reactions, and remember that you might be asked for a different reaction. Any questions so far before we go and take a look at the report? Okay, so let's share the report. Okay, every person has a different data, so you cannot have the same data as me. If you were in the lab, you have to complete all this exothermic reaction, but in this case, you are given with all this data. So the first one, it says, describe the reaction of copper wire and nitric acid, but read it to become familiar, because you actually will need it to respond to the question. So they tell you exothermic, all this is done because there is no way for you to guess if you don't do the experiment in the lab. So the first thing that you have to do, they give you all the data here. And the first thing you have to do is to calculate the mass of the recovered. This is that whatever is in green is what you will have to do. We saw in our example how to calculate the mass of recovered copper. With my numbers, how would you do it? Can you send me a message? How did I obtain the 0.117? Same as I did it in the example, in the learning check that we did together. Exactly. Thank you, Emily. Exactly. We subtract. Awesome. Douglas is saying 37.722 minus 37.605. Perfect. That is correct. Very good. And how do I get the percent yield? Once I have the recovered copper, what did I do in the example? The mass of the recovered copper times 100 divided by the original mass of copper, which is 0.12. And that's how I obtained 115%. Note that my percent yield is higher than 100, which means that I probably didn't dry my copper correctly. Cannot be higher than 100. And then you will be asked, they will give you the first part of the reaction, and you will need to complete it. Basically, all the reactions are given in the background when you read the experiment, so you will have no problem to complete this report because all these reactions are given. And then here we are asking, after the question that I was mentioning before, after heating the solution, you decant the liquid and wash the remaining solid with distilled water. What are you removing by this washing? And we said that we are removing what? Do you remember what we said? The first removing. Somebody? Yes, thank you. Perfect. We are removing the sodium nitrate. That's correct. And then they say, after adding sulfuric acid, what copper compound is present in the beaker? All we have to do is look at the reaction, right? When we add sulfuric acid, we add the sulfuric acid to the black copper oxide. Let's look at the reactions here. Okay, the reaction there is not asked. Let me see here. Okay, so what is the reaction of sulfuric acid? You have it in your it's basically the reaction number 4 of the 5. So you will look at this reaction and it says, after adding sulfuric acid, you add sulfuric acid to the copper oxide, what copper compound is present in the beaker? You can tell me by looking at this reaction. Exactly. Thank you, Douglas. This is what we have, the copper sulfate. Very good. Then to complete the balance equations, you have all the balance equations. And then they ask you, after adding zinc, what compound is present in the solution? You have the reaction here. So if you add zinc to the copper sulfate, yes, thank you, exactly. In the solution, we are going to have two things, a solid, that is the copper, and the solution of zinc sulfate, that we said that we won't stop until it's clear, because the other solution of copper sulfate was blue, and this one has no color. And then they will ask you, I wrote here hydrogen gases. Okay, no. After adding zinc metal, what is the gas product? We said that reacts with the acid and forms what? Exactly. Thank you. Yes, that is correct. Hydrogen. Very good. And then they ask you, how can you firm? We know that the hydrogen is flammable. If we lit, it's not written right there, but if we lit a splint and held it near the opening of the tube, if it's hydrogen gas, it would ignite because it's flammable, because it's also colorless and has no odor, but because it's flammable, we can do that. But you can okay, so this would be that, and then what else? After adding zinc metals, we said, how can we confirm? And the last question, when washing the solid after the reaction with zinc, what are you removing? We have to look at the reaction. What are we removing? We add zinc, and what do we have? And we want only the copper. What are we removing? Removing the zinc sulfate, because we don't want that. We want the copper clean. And basically that's it. The last reaction is about what we talk about if the recovery is higher or recovery is lower than 100, and by now you will figure it out what to answer. Any questions so far? Okay, so this is a nice stopping point. I hope this was helpful. I want to thank everybody for listening to me, and I will stop the recording and stay in case you have questions regarding this experiment or previous experiment. Thank you again.